Hi everyone, welcome back. This is the second part of the video on continuity. In the first part we looked at the definition of continuity and some examples. So if you haven't seen that part, go and watch the first part of the video. In this part of the video we're going to look at some more consequences of the definition of continuity and then one of the major theorems about continuous function. So one of the things that we observed in the last video was when we're taking the limits of functions, some of them are easy to take. You can just take the value of where you're taking the limit to and pop that into the function. And in some sense, continuity the definition of continuity is saying that those are precisely the continuous functions, where the limit is equal to the function value. In our experience with taking limits, we've seen that a number of types of functions have this property, that the limit is equal to the function value. In other words, they're continuous. And here's a list of them. All of these functions are continuous, and here's something to observe on their domain. So polynomials, rational functions. Rational functions are continuous on their domains. You may think, well, some rational functions are discontinuous, like 1 over x, for example. 1 over x looks like this. So there's our function, so coming down. There's our function y equals 1 over x. You may say, well, that's discontinuous at 0. It certainly is discontinuous at 0, but 0 is not in the domain. So I'm certainly free to say that the function 1 over x is continuous on its domain, because its domain doesn't include 0. But you're also certainly welcome to say that the function is discontinuous at 0. You're just saying something about how the function is behaving at a point or near a point that's not in its domain. That's fine. Just be careful that I'm talking about continuity of all these functions on their domains. So root functions, square roots, cube roots, etc., those are continuous on their domains. Trigonometric functions, inverse trigonometric functions, exponentials and logarithms, all of these functions are continuous on their domains. Now, we've seen that with all these elementary functions that we have here, we can start combining them in different ways, adding them, multiplying them, composing them, using function composition. We can create new functions in this way. How does continuity behave with those ones? Well, this next fact tells us that if f and g are continuous at a, and c is just some arbitrary constant that we're going to use to multiply to these functions, then the following are also continuous. Adding two continuous functions is continuous. Subtracting two continuous functions results in a continuous function. Scalar multiplying a function by a number, still continuous. Multiplying two functions together that are continuous, they're still continuous. Taking the quotient of two functions, f divided by g, they're continuous on their domains provided g is not 0. So the ratio, in some sense, if f is continuous on its domain and g is continuous on its domain, then the ratio is continuous on that new function's domain. Those are the places where you have to ignore the places where the bottom or the denominator is vanishing. How do you prove these results? We've got the definition of continuity. That's that the function is continuous, that the limit is equal to the function value. Now I'm saying that we can combine continuous functions to get more continuous functions. How do we prove that f plus g is continuous if we know f and g are continuous? Well, these are just following from limit laws. So these follow from the limit laws. I'm just going to look at one proof, just so that we sort of clear up loose ends. I'm making a statement here in general about continuous functions. I kind of want to show you that we can prove these things rigorously if we need to. So I want to show that the limit as x goes to a of f of x plus g of x is what? To show that this function is continuous, I need to show that the limit as x goes to a of the sum is equal to f of a plus g of a. Well, we have one limit law that says if we're looking at the limit of the sum of two functions, we can take the corresponding sum of their limits. And now, at this point, so this is one of the limit laws. At this point, what's the limit as x goes to a of f of x? Well, we know f is continuous. That's one of our assumptions here. F and g are continuous. So this just has to be f of a. What's the limit as x goes to a of g of x? Well, g is continuous at a, so that's g of a. So this is equal to f plus g of a. So the limit of the sum is the sum of the limits, essentially, and this is then telling me that the function f plus g is a continuous function, because its limit is equal to its function value. Okay, so all these other ones follow from the limit laws as well. So let's look at this example. We've got a piecewise defined function and two parameters a and b. We'd like to find the values of a and b for which this resulting function is continuous. The first thing to observe is that each of the pieces is continuous on its domain. This is a square root function minus 1 over a linear function. We saw in the previous slide that taking the ratio of these kinds of functions, well, they're continuous on their domains in the places where the denominator is not vanishing. The only problem that occurs with this is where the denominator is 0. But if I look over here, 0 is not in the interval I'm considering. It's one of the endpoints which I've excluded. So this is continuous on the interval 0 to 1. Similarly, this rational function for that third piece, it's continuous except at the places where its denominator vanishes, possibly where its denominator vanishes. And those are the values where x is 0 and x is negative 1. But those are also not in the interval I'm considering. So this is continuous on this interval. So really the only places where these discontinuities can occur are where I'm trying to match these things together, where I'm trying to glue these pieces together to form this piecewise function. Where are those sort of gluings happening? They're happening while I'm running from negative 1 to 0, and then I jump to another piece from 0, and then I jump again. So really the gluing's happening at 0. So I want to check, is it continuous at 0? That means I want to check, is the limit as x goes to 0 of f of x equal to the function value there, f of 0. So what I need to do is I need to check, what is the limit as x goes to 0 of f of x? And in order to do that, well, it's defined differently on both sides of 0, so I really should be considering left and right-hand limits here. So the first thing I'm going to do is look at the left-hand limit. That's as x goes to 0 from the left of bx to the fourth plus bx all over x squared plus x. As x goes to 0, both the numerator and the denominator are heading to 0. So I need some algebraic simplification first before I can compute the limit. And there I just notice there's a common factor of x both in the top and bottom. So I factor out that common x factor, which leaves me with a bx cubed plus b on the top and an x plus 1 on the bottom, and therefore our limit is b. So our left-hand limit is b. What about our right-hand limit? Our right-hand limit is the limit as x goes to 0 from the right of the square root of 1 minus x minus 1 all over ax. And what's happening here? Well, this is going to 0. Maybe I'll put this in a different color. The denominator is going to 0. The numerator is going to 0 as x heads towards 0 from the right. So I'm going to, again, need some algebraic simplification, if possible, to try to get this down to an expression where I can then pop in 0 to evaluate the limit. In order to do this, we notice that, well, x is a factor of the denominator. Since the numerator is vanishing, maybe x is sort of hidden as a factor in the numerator. How can I get it to show itself? How can I get x to show itself in the numerator so that I can cancel it off? Well, one way is to multiply by what's known as the conjugate of that expression in the numerator. So it's a square root of 1 minus x minus 1. I'm going to multiply by the square root of 1 minus x plus 1. The rationale behind doing this, maybe I'll put this sort of in a little thought bubble here. The rationale behind doing this is if I have an a squared minus a b squared, that factors as a plus b, a minus b. So what this says is that if I have either of these expressions, an a plus b or an a minus b, I can multiply by the other one and put squares on the a's and b's with a minus sign between it. I'd like to get rid of that square root. So if I multiply by the same expression with a plus sign between it, then I can replace it with the expression where I've got squares on each of those quantities, and thus eliminating the square root. So that's the rationale behind doing this. So when I multiply these two out, I get a 1 minus x. That square root gets squared, so it leaves me with that 1 minus x. And then I get a negative 1 times a plus 1, which leaves me with a negative 1. If we were to multiply the cross terms, you'll see that they cancel. So that's really why there's only 2 terms survive. Normally you'd get some cross terms here when multiplying these two expressions, but they will cancel out. The denominator, that's ax times the square root of 1 minus x plus 1. Now if you look closely, as x goes towards 0, well, we're not out of the woods yet. We still got x on the bottom, but we get some cancellations occurring. I've got a 1 and a minus 1. Those cancel off to leave me with just a negative x on top. That negative x is the hidden x that we were trying to find to cancel off. So it cancels off with the 1 in the bottom. And now we can compute the limit. As x goes to 0, this becomes 1 minus x, or 1. Square root of 1 plus 1 is 2, so this becomes negative 1 over 2a. And the last bit we need in order to check continuity is what is the function value. So the function value at 0, and that is 1. What do we need? In order for it to be continuous, we need that the limits, left and right hand limits, are equal, so that the limit in general exists, and that the limit equals the function value. So we need, so f is continuous at x equals 0 when the limits, left and right hand limits, are equal to each other and they equal the function value. And so that means then that we need b to be 1 and a to be negative 1/2. And if we have b to be 1 and a to be negative 1/2, then we've got a continuous function. So let's just have a look at this. Here we've got our function sketched, and I've got these parameters a and b that I'm allowed to change. Function value is 1 there. What I was trying to do was come up with values for a and b for which the function becomes continuous. So I need to choose b so that it hits there. Okay, so b is 1. b is 1 makes that piece of the curve hit the point. What about the a value? I need to get it to match up as well. So there we go, it matches up. A had to be negative 1/2. So when I choose a and b to be these values, the curves match up at that point. And that's what we found. That's what we found right here. We found those values of a and b for which those curves match up. And therefore it's continuous. So now let's look at how continuity behaves under composition. So suppose f is a continuous function at b, and the limit as x goes to a of g of x is b. Then if we look at the composition of f composed with g, the limit as x goes to a of f composed of g of x is just going to be f of b, namely f of the limit as x goes to a of g of x. Okay, so how do we actually use this? It might look a little bit confusing, but it's actually very straightforward. What this says is that when we're looking at the limit, in this case, as x goes to 0 of e to this thing, we have to realize that this is a composition. This is a composition of an outer function, which is the exponential function, and an inner function, which is what's going on in the exponent there, 1 minus x minus 1 all over x. It's a composition of those two. And this result is telling me that if I want to evaluate the limit as x goes to 0, I can really just pop that limit up top. So I can look at this as being, well, it's just e to the limit as x goes to 0 of the square root of 1 minus x minus 1 over x. So now I just need to work out this limit. So maybe I'll just work out that limit here. We'll look at the limit as x goes towards 0 of the square root of 1 minus x minus 1 all over x. What is it? Well, it's of type 0 over 0 again. As I plug 0 in, top and bottom, they both go to 0, so I'm going to need to simplify it first. How can we simplify it? Well, it's very similar to that previous example. We can multiply by the conjugate of the numerator to get rid of that square root by putting it downstairs, but now with a plus sign between the root and the 1. So this becomes 1 minus x minus 1 all over the square root of 1 minus x plus 1, and that's times x. These 1's cancel off. The x's will cancel off. So we get that the limit as x goes to 0 of negative 1 over the square root of 1 minus x plus 1. Now we're in good shape to evaluate the limit. As x goes towards 0, this becomes a negative 1/2. And so that means, back here in our original expression, the limit of e to that expression is equal to e to the limit of the expression. We've now calculated that limit, so this is just e to the negative 1/2. And so there's our answer, e to the negative 1/2. So that's what this is telling us, this theorem above. It's saying that if the outside function is continuous, then you can always push the limit on the inside and then focus on working out what the limit of the inside function is. This next result is about the composition of continuous functions being continuous. So if g is continuous at a and f is continuous at g of a, then the composite function f composed with g is continuous at a. Let's actually give a proof of this. We know what the definition of continuity is. It means that the limit has to equal the function value. So what we're going to do is we're going to look at what is the limit as x goes to a of the composite function, f composed of g of x. And what we're hoping to get out at the very end, if f composed of g of x is continuous, then the limit better equal the function value there. So that better equal f composed of g at a. That's what we want to get to. Now if I rewrite what this means, it just means that f of g of a. So the composition means, you read from right to left. G is the first function that's applied to a and then followed by f. So I need to get from here to there. What's the limit as x goes to a of the composition? Well, let's first rewrite the composition in terms of what it means. It means that we're applying g first, and then we're applying f after. Since f is continuous at g of a, and the limit of as x goes to a of g of a exists, since g is continuous there, then we have that this is f of the limit as x goes to a of g of x. So this result is by that previous theorem. Let me just back up to it. Previous page. This was telling me that I can push the limit across f and inside it as long as f is continuous at b when the limit of g of x as x goes to a is b. So it's saying I can push that limit inside. So I'm just using that previous theorem to get this step. So by continuity of g at a, this is g of a. Continuity says that the limit is equal to the function value. So this is since g is continuous. And well, I didn't need that extra line there because I already had it, so let me just scratch that out. And therefore, we've got exactly what we wanted. So now we have that the composition is continuous. So this is essentially how you prove these kinds of theorems. You want to show something's continuous, you go right back to the definition. Look at the limit, see if it's equal to the function value. So this brings us now to one of the most important properties of a continuous function. This is known as the intermediate value theorem. It's best to look at this in terms of a diagram first. So what I have is, I have a function f, and let's suppose it's continuous on the closed interval a to b. And I know that f of a, that's some value, let's call it f of a here, f of b, that's some other value, and I'm just assuming that f of a is not equal to f of b. That's what it says in the statement here. And I let n be any number in between. So there's n. And so here's the question. The function's continuous on this interval, so as I start to sketch it, I'm going to have to be able to get from this point up to this point without lifting my pencil. That was the intuitive idea of what we captured with the definition of continuity. Can I do that? Can I sketch the curve from here to here without lifting my pencil and not touch this line? Or must I have to actually touch this line through big N? Well, as I go along, I can sort of avoid the line as much as possible, but at some point, I'm going to have to cross in order to finish drawing. So at some point, I have to cross that line. Let's call that point, that x value, C. I could maybe cross more than once, but the theorem, the intermediate value theorem, says there has to be at least one point where you cross that line. Call it C. And that's the intermediate value theorem. It says that if you have a continuous function on an interval a to b, and you pick a number, capital N, any number between f of a and f of b, the function has to take on that value for at least one value C. There could be more, but it has to take on at least one value. So here's the visualization of the intermediate value theorem. So this is such an important property of continuous functions that there have been some comics that have sprouted up about this, and I particularly like this spiked math one. So let's use the intermediate value theorem to see what kinds of results we can get from it. I really like this result. Use the intermediate value theorem to prove the square root of 2 exists. This is just showing how powerful the intermediate value theorem is. Notice I haven't proved the intermediate value theorem. We haven't discussed a proof of it. I just sort of gave a diagram that suggests that it should be true. We haven't proven it in any rigorous way. This should suggest that proving the intermediate value theorem is a very deep result in math, because from it we're able to deduce things like the square root of 2 exists and other properties, as we'll see throughout the course of this term. Very powerful theorem in math. Where you would see a proof of the intermediate value theorem is in a course in real analysis. We have one here, Math150. There you will actually go through a lot of the major theorems we've seen in calculus and prove them from a rigorous standpoint. It involves going back and sort of building up the integers and rational numbers and real numbers from basic principles, and then getting to major results like this. But for us, let's just see how powerful the intermediate value theorem is. I want to prove root 2 exists. Okay, so what does that mean? You may think, well, what do you mean by root 2 exists? Well, what I'm really asking is, let's prove that there exists a number so that when you square it, its value is 2. Let's prove that there exists a number so that when you square it, you get a value of 2. If you want to think, well, you might be thinking that's obvious. It's the square root of 2. Well, that's a name we gave to this number, but we had to know it existed first before we could give it a name. As an analogy, I could say, give me an example of a number so that when you square it, the answer is -1. You might be thinking then, well, anytime I square a number, it's always positive. So there is no number that when you square it has a value of -1. Well, that's right. There is no real number when you square it has a value of -1. This is sort of in the realm of believability that there is a number when you square it gets you a value of 2, but we still need to prove that. I need to prove such a number exists. So how do we do that? Well, part of it's here in this statement. C squared is equal to 2. So what I'm going to do is I'm going to consider a function. F of x is equal to x squared minus 2. Now, what is a root of this function? What is the value of x for when I plug it into this function has a value of 0 coming out? Well, the answer would be root 2. If I plug root 2 in and I square it, subtract 2 from that, I get 0. So the question about the existence of root 2 is really a question about showing there is a value of x for which this function takes on the value 0. Let's get a sketch of this. X squared minus 2, so that's the x squared function shifted down 2 units. Looks something like this. So that's y equals f of x. What's happening? Well, I'm trying to show that there is this point here, this x value. I'm trying to show that that exists, that there is this value root 2, because the value of x for which the function crosses the x-axis is going to be this value that I call root 2. How do I know it exists? Well, let's consider this function. F is continuous on the interval 0 to 2. What else do we know? Well, what's the value at 0? Well, f at 0 is negative 2. What's the value at 2? Well, that would be 2 squared minus 2, or 2. So takes the value negative 2 down here, and then over here at 2, it takes the value of 4. The intermediate value theorem. So this is a continuous function on the interval from 0 to 2. It takes a value below the x-axis, or below y equals 0. It has a value that's above the x-axis, a y value of 4. If I want to connect that point to this point, by sketching the curve, there has to be a place where I cross the x-axis. Intermediate value theorem. By the intermediate value theorem, there is a c value in the interval 0 to 2, in the open interval 0 to 2, so that, or such that, f of c is equal to 0. Intermediate value theorem says I have to cross the x-axis. There exists this value c. That's the value we call the square root of 2. So c exists. C exists. We call c the square root of 2. So the square root of 2 exists. There exists a 0 to this function. We call it root 2. So that's how we can use the intermediate value theorem to prove some pretty deep result in math, that the root 2 exists. Deep result in the theory of continuous functions. Let's use the intermediate value theorem to show that this equation has at least one real root. One real root. A value of x for which e to the x is equal to 2 minus x. Well, again, let's consider a function which is the difference of the two. E to the x plus x minus 2. So I'm just going to move everything to one side, so I get an equation equal to 0. And now, this is equivalent to showing, so we want to show f has a root. A value of x for which when I plug it into f of x gives me a value of 0. So how can I find this root? Well, first note that f is continuous. It's continuous everywhere, the whole real line, so it's continuous on R. And that means if I consider any closed interval of R, it's still going to be continuous on that interval. Let's see what interval we can get to sort of make sense of things. E to the x is getting big fast. So maybe if I look at, I know if I take x big enough, e to the x is going to be huge. So eventually I can get e to the x to overpower x minus 2. So let's try to look for values for which e to the x is small. If I take 0, for example, that becomes e to the 0 plus 0 minus 2. So that's 1 minus 2, or negative 1. So I've got the function value negative somewhere. Where is it positive? Well, what if I take x to be 1, for example? Then this is e to the 1 plus 1 minus 2, or e minus 1. And if we remember that e is a number slightly bigger than 2, so this we already know is positive. So if there's a place where the function is negative, there's a place where the function is positive. So by the intermediate value theorem, there is a c in the interval from 0 to 1 such that f of c equals 0. In other words, e to the x equals 2 minus x has a root in the interval 0 to 1. So we know there's a root there. We don't know what that root is. Notice here, this is the power of the theorem in some sense. It tells us that a root exists. It didn't tell us what the root was. We don't know what the value is. But it tells us that such a root exists. Now that we know it exists, we may want to try to go and look for it using other techniques or something. But we know it exists. All right, so that's it for this lecture on continuous functions. Thank you very much for watching, and we'll see you next time.